Okay. All right. And so as I was saying, these are all recorded. Yeah, so I think that's it before we get into this intro stuff. So for the intro today, this is the part that I printed out for you, so you don't need to write all this stuff down, but these are my recommendations for how to study for and pass this course. At this level, sometimes people don't have like really what you call like rigorous systems to pass a class. This is an example of a good system to pass this class, right? And by system, I mean your instructions to yourself, right? So, so as I say at the top here, your study habits for this course can be really formulaic, right? Every class period, we go over either 1 or 2 sections, and then there's a homework assignment associated with those sections, right? And so it's gonna be roughly the same thing we do in class every day. So your first task is to read that chapter, or at the very least, skim that chapter before you come to class, right? You know, I can't really like assign this as homework, but if you'd like to understand more about what's going on in the class, it helps to read that book. And at first, it might be really difficult because not many people are used to reading textbooks. It's kind of boring sometimes, right? But what you'll find is that you get used to it. And if you're able to read a math textbook, then you can read a biology textbook, a chemistry textbook, or anything else, right? And so if you practice on math, which is difficult to read the textbook for, other textbooks become easier to read. So go ahead and make sure that you read the chapters before the classes. One thing you'll want to do, whoops, let's see now. There we go. One thing you want to make sure that you do is at least write down everything in the green filled boxes. And so I have this little picture of our book here. I'm just going to zoom in. You can see here, this is like in chapter 2. It says the associative laws, right? Like stuff in these kind of boxes, you should write that down. That's the most important stuff that's in the chapter, and that's going to be the roadmap to completing all your homework problems. Okay, some chapters are full of those, some chapters only have a few, but you'll definitely want to pay attention to those. So after you read all this, this is going to prepare you to come to class and ask questions about stuff you don't get, right? You know, it really helps if it's the second time you hear it in class, because then you can really pinpoint like what you're not quite sure about, and I can answer specific questions about that. All right, and I always tell everybody, like, you know, you got to learn these concepts over and over. At least that's what it's going to seem like. You're going to read it in the book. You're going to hear me blab about it. Then you might hear me blab about it again over in the Student Center. And eventually this stuff starts to sink in and it locks in and you get it. Okay, task 2, attend all the lectures. This is pretty obvious, but small gaps in your knowledge, this can cause ripple effects in math. And so if you miss the lecture on maybe a rule of an exponent and you just sort of forget about that, that might come up later and we'll all just talk about it like we understand it. I'll move right over it and you'll be sitting there like, what the heck does that even mean, right? And so be careful about missing lectures. If you miss a lecture, make sure you watch the video if it's available. Do extra homework problems. This is going to be big this semester. And the reason is because this first homework assignment sheet has a lot of problems on it, but I really want to pare these down and leave most of the individual study a little more up to you. So your homework assignments will be like half the usual size, but you'll be required to go and do the extra problems that you need to do on your own. Okay, so, oh, and if you don't fully understand a problem during your homework, I think I just said that. Yeah, it's your responsibility to go and practice that. If you're wondering where to find practice problems, come talk to me. I got a ton of websites I can just print out random ones from. I can point some out in the book. You know, I can support you in any way when it comes to that. When it comes to those difficult problem types, keep track of them. So if there's like a problem type that we go over this week that you struggle with, make sure you write it down somewhere and remember it, because when it comes time to study for the next exam, you're going to want to focus on that. Okay? All right. Task 4, come and see me or another math faculty on a fairly regular basis. This is just to get clarification for anything you might not be sure about. Even the smallest little thing, come and get clarification on it. And here is a note about how much time you should expect to be spending on this class. So the general rule, I wrote way too much here. Here, ignore that and pay attention to what I'm about to say. So the general rule is for every credit hour that you have in a class, you should spend about 3 hours per week on that credit hour, right? And so we have a 3 credit, or is this 4 credit? This is a 4 credit class, right? Yeah, so you're expected to spend 4 hours per week in class and then 8 hours per week outside of class, right? That works out to 3 hours per credit hour. So, you know, I mean, your homework might take you 4 hours, maybe. That means you got 4 whole hours to either read the chapter or study extra problems every week, you know, and so don't forget to do that. Make sure you're studying some extra problems. Okay. Now we're going to go over how to do homework. So this book, they printed it kind of interesting. They linked all the homework sections to a specific chapter in the book. And so I'll show you how this looks. So of course, read the chapters, take notes. This is what your homework section looks like. So notice here, let's say I assigned you problem number 30. And suppose you didn't really know how to do problem number 30 and you were stuck and I wasn't around, nobody was around. Well, you'd look up at its heading. See how this heading says associative laws? So that you'd go back in the chapter and you'd flip to section B, which is all about the associative laws. And section B should have the rules that are going to help you solve this, and it should also have a couple examples that are similar to this. Okay, and that's usually, at least when I was first studying math, like the examples in the chapter were, you know, I would always flip back. How did they do it in the chapter? Can I do that the same way in the homework? Okay, so that you can do a lot of flipping back and forth. And this is everything I just said. Yeah, so, right, this is associative laws in chapter 1.2. This is where I'd turn if I had a problem in the associative laws section that I couldn't figure out. Okay, right, and you can see, like, if it was in section D, you'd turn to the page with section D on it, and you'd read through that and see how to do the problem. Sometimes they'll be in multiple sections, and so they'll have, like, you know, section A and B, and you might need to read them both. Just so you know, this is really helpful. All the answers to odd numbers are in the back of the book. It's killer, right? So there's 2 things that means. That means that when I assign an odd-numbered problem, I want to see your work on that, right? Don't give me just an answer for an odd-numbered problem, because it's really easy to be like, see where that came from. But also, this is really helpful if you're not sure if you're doing an even-numbered problem correctly, right? And so if you're working on number 30 and you got an answer, and you say, I'm not sure if I did that right, do number 31 and check your answer. Right? If you got it right, you're good. Maybe even try number 29, check your answer again, right? And so that's how you can get problems with the answers. Do the odd ones, and then come back and apply that to the even ones. Okay, so that's all in the homework and all that kind of stuff. So now we're going to finally jump into the chapters here. And I'll go ahead and warn you guys, the first chapter of this book really feels disconnected in a lot of ways. And so we're just going to be studying all sorts of different topics. I'm going to be throwing a lot of definitions at you guys. We're going to talk about fractions and variables, but it kind of feels almost random, like topic after topic. Around the second chapter is when it all starts to tie in a little better, okay? All right. Any questions before we move on? All right. Oh, and I didn't mention this. I forgot 2 things, actually. 3 things now that I think about it. First of all, I forget things sometimes. That was the first thing. Second of all, I really like to laugh and joke around in this class. I'm a total goofball for anybody who knows me. So it's okay to laugh. It's okay to laugh at me when I make mistakes up here, because I will, without a doubt. If you see me make a mistake, it's okay to say, hey, hey, you missed that 2, or you dropped your negative or whatever. It's totally fine. I make a ton of mistakes. That's just the way I do math. I'm not a perfect mathematician. And honestly, like, anybody who doesn't make mistakes when they do math, like, I don't think that's a realistic mathematician. That sounds like a fake mathematician to me. We all make mistakes. The difference between a good and a bad mathematician is that when you make a mistake and you're a good mathematician, you learn from it, right? Mathematicians who just make mistakes and then forget about them and move on, it's not a good mathematician. And the other thing I forgot is introductions. So I'm Louis Scott. I grew up here in Ketchikan. I got my degree on the Juneau campus. I graduated high school here and messed around on construction sites and on towboats for about 10 years, and then was like, hey, I should go get my degree. I didn't know I had no idea I even liked math. And I got into some math classes, thought it was interesting, jumped into a calculus class, and immediately dropped my business degree, jumped into calculus, and never looked back. Did I know I was good at math? No. Did I get good grades in math in high school? Nope. What really made the difference was that I was enthusiastic about the subject. When I failed at things, which I did frequently, I just kept getting up and going, right? And that's really what it takes. I'm married. I have a dog and a cat. And what else? I play video games for like an embarrassing amount of time every week. Okay, so you guys want to introduce yourselves? You want to go first?
I'm Erica. I graduated in 2017. This is my first year of college.
Okay.
Yeah.
Cool. You don't have to go into a big spiel. It's okay. Go ahead.
Are you looking at me or the person behind me?
Sorry, you go ahead.
like a straight shot.
Right?
I'm Tyler Lynn. I'm covered in paint and
right.
fly sticky stuff. I live here, born here, and that's it.
Awesome.
Yeah.
All right.
Don't judge the paint.
Right.
Paint.
I'll try and overcorrect from now on. So if you see me looking here, that means you. Just kidding. Right? Jen?
I'm Jenica. This is my first real year in college. I got my CNA license, so I got a location for 6 months. And now I'm going to get my nursing degree.
Cool. All right.
Oh, I'm Danny. I am 2 semesters away from being done. I put math off till last.
Oh, boy.
I dropped out of my first year because math and I don't see eye to eye, which is why I became an accountant.
Ah, very good. Very good.
We can get mad together. I work for KPU. I bring in all the money, which is kind of comical, but I work in software and systems.
Ah, okay. So you work well with, do you know what an algorithm is?
Yes.
Well, yeah, so you work well with algorithms. Okay, I'm going to remember that. All right.
But like Y's and X's, and my brain just goes, the purple elephant and the orange suitcase ran for what? Shut down.
Ah.
So, yeah.
That's actually, so we don't necessarily want your brain to completely shut down.
Yeah.
But the moment of struggle when you think maybe I can't do this, but you keep going, right? And you work your way through that problem anyway. That's actually what we're striving for in this class, because it's at that moment when you're not only learning the math, but your brain is expanding. They've done these interesting studies with brain scans that shows that people who have studied mathematics intensely within the last 6 months, there's a little node in the front of your brain that they think, they don't know, they think it's associated with hardcore logic and reasoning. However, they also think that it has nothing to do with language, which is very interesting. And they showed that if you study mathematics intensely for like the last 6 months, blood just pumps into that little node, and it increases, like, it's like a little muscle, right? And so it's like, yeah, and that's really like, that's the way to look at this, right? Like, math, sure, there's the numbers and stuff, yeah. There's all that. But there's the logic, the hardcore reasoning that is going into this, right? This is isolating your logic muscles in your brain. Just like if you want to grow like your biceps or something like that, what do? You max them out, right? You lift so much weight to where it breaks them down and they have to rebuild. Right? If you wanna run up a mountain, you don't start by running straight up that mountain, do you? You start out in pain at the first 100 feet of that mountain. If it's me, it's the first 50 feet and you're doubled over going, oh my gosh, how do I do this? Slowly, through pain, you work up, right? And that's what we're doing here too. So it might not feel pleasant all the time when you run into a really difficult math problem, but when you feel that bit of unease, it's not a bad thing, okay? So if you guys haven't noticed, I like math a lot. Okay, so let's go into the section 1.1 here. The first little bit here, I gave you a handout so you don't have to write all this stuff down, but these are all the definitions that we're going to be dealing with when it comes to algebraic expressions. So we're going to explain algebraic expressions through this first example. So the first example says, suppose we have some concert happening in town. Let's also suppose that this concert costs $90 for one ticket. That better be a good concert. Okay. So now let's suppose the letter N, that represents the number of people who bought tickets to this show. If we assume both of those things, then we can say that the total money taken in from tickets can be represented by this expression, 90 times N. Sometimes I use this little asterisk for a multiplication sign. So if you see that, it means multiplication. Okay, so let's go over the definitions contained in this expression. So the letter N, that's called the variable of this expression, right? It can represent any one of a set of numbers. The number 90, that's called a constant term. That doesn't change, okay? The multiplication sign, that's called the operation sign. The expression, 90 times N, that's called a variable expression because it contains a variable. An algebraic expression, that one consists of variables and or numerals, often with operation signs. And so I'm going to put a little star on this next one. This one's important. We're actually going to do, I'll tell you right now, there's a problem on the final exam where you do exactly this. When we evaluate an algebraic expression, we substitute a number in for a variable and calculate that result. Right? So if we were going to evaluate 90N, we'd say, well, what if 10 people showed up? We'd plug in 10 for N, say 90 times 10, and that would give us 900. So I'll put a little star next to that evaluate definition. The next is called the value. That's the result of the evaluation. Right? And so if I was to evaluate 90N, suppose N was equal to 10, right? I would just substitute 10 for N. That is equal to 900. Right? And so this part, this side would be the evaluation. This side would be the value. Okay? This next one, put a star next to this one as well. This one's not actually in the book on this chapter. But this one comes up all the time, and it's it's something that I don't know, it's something I use all the time in class, and I think this is one of the most forgotten definitions. This is called the coefficient, right? The number 90 in this expression is called the coefficient, and that's whatever number is attached to a variable through multiplication. Okay, so those are the definitions of a basic algebraic expression. All right. Next. Here are some examples of how you evaluate. And you know, even though the evaluation question on the final exam will be more complicated than this, it works the exact same way. When I say evaluate, I like to call it plug and play. Right? You plug in the numbers and then you calculate and then you're done. That's what I like to call evaluation. So I have an expression. x plus y, and I have values for both x and y. To evaluate, I just plug them in and calculate. So I'm going to replace x with 37. I'm going to replace y with 28, and the plus sign just stays there. Let's see now. What is that? 50, 65? By the way, I'm bad at arithmetic. I will usually rely on you to tell me if I'm incorrect. And even small calculations, I love to use my calculator. I don't like arithmetic. I like abstract, weird math. Arithmetic bothers me because I'm bad at it.
Well, it's a waste of time.
Right? Everybody's got a calculator. Yeah.
It just takes a little longer.
I agree, yeah. I'm like, come on. Yeah.
If you really want to do long division, anyone can.
Yeah, what person doesn't have a calculator on their phone in their pocket? Yeah. Yeah, so that would be how to evaluate that first one. You can see this next one's not too different. We're just using multiplication instead of addition. Oh, and by the way, I'm not sure if you've seen this kind of notation before, but in algebra, when it's obvious that things are multiplication, it's always multiplication. And so this says 5ab. You know, there's no multiplication sign here, but the one is implied. So 5b means 5 times b, right? We don't always write the multiplication sign. So for this one, they say assume a is equal to 2, b is equal to 3. So I would say 5 times 2 times 3. And if you're not sure why I'm using those parentheses, it's just because that's the way I write things. I could also write it as 5 times 2 times 3. The little dot means multiplication as well. Sometimes I'm not sure what you guys have seen so far. Okay.
I just finished up an 054 over the summer, and he, for the whole semester, had to stick with one or the other so that we weren't confusing ourselves.
Gotcha. I might let you guys be confused. I'm not that strict. But you know, yeah, just get used to it. Yeah, other things that are different than 054, we don't use mixed fractions here because they're completely confusing, right? Because it, you know, and it's because of this rule, right? This says 5 times a times b. So if I said 11 and 3/4, whoops, that's not 3/4. Whoa, back it up, back it up. If I said 11 and 3/4, does that mean 11 and 3/4 or 11 times 3/4? Right? That doesn't make sense in algebra, so we don't do that. Right? If you see that in algebra, it definitely means 11 times 3/4. Okay? If you want to write it in mixed fractions, put a plus sign in the middle. We just leave them improper here. We love improper fractions. They're great. Okay, the next one. The area of a triangle with a base of length b and a height of length h is given by this formula. A equals 1/2 base times height. Now it says, find an area of a triangle when the base is equal to 8. Okay, I'm just going to write that down here so I don't forget it. B equals 8. And the height is equal to 6.4. H equals 6.4. Okay, so now I'm just going to rewrite the formula. A equals 1/2 base times height. And then I'm going to plug in my base and my height. 1/2 times 8 times 6.4. And things cut, right, and you can see when I have this 6.4, I got to be careful that I don't confuse this with multiplication. You know, if you want to be sure for your own notation, that's maybe why I like the parentheses. Right? If you just put parentheses around it, that means multiplication. So 8 times 1/2, that equals 4. So I have 4 times 6.4. I'm just going to punch this in the calculator because like I said earlier. And we get 25.6. Okay. Units. I'm not a huge stickler on units in this class. It's good practice to do the units, but if you're missing units on an exam or something, I'm probably not going to take off points. However, when you get up to Colleen's class, she might, which is why it's not a bad idea to practice. So for this one on units, you would have meters squared. And that'll make sense when we get into the square sections. Or even just meters would be fine on this one. Okay, so those are our 3 evaluation examples. Now let's go into translating algebraic expressions. And so this is all about like word problems. So if you struggled with word problems in the past, I know I have. I hate them. They are the worst kind of problem that I can personally run into. If you struggle with that, make sure you study this stuff a little bit extra. Okay, and so this is kind of like how to convert English into math. Okay, so one of the most important things is how to identify the variable in the problem. So when we're talking about some sort of word problem, like, a word problem might start out by saying, like, what height is the bridge, right? What? That means the bridge's height will be represented by x in the problem, right? These are all variable indicators. These indicate a variable, right? If I say, how many apples will it take, blah, 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 blah. That means apples will probably be represented by x because it says how many apples, how long, right? When the problem is asking a question about a quantity, that usually means that quantity is going to be represented by an x or a y or some other variable. Okay, so here's a table from page 4 of your book. I would recommend that, I'd recommend that you read through this later. We'll do just a couple of the first examples right now. But this is the kind of thing that's definitely going to help you to get your head kind of wrapped around the whole English to algebra thing. The way that we read this, we just go across each line. Right here is the indicate, like the keywords. This is how it would appear in a sentence. This is how you would define your variable for this sentence. And then over here is the final algebraic translation. So this first line, you can see it says added to. And so if you see that in the middle of a problem, it indicates addition. That's pretty obvious, right? 700 pounds was added to the car's weight. If they asked us to convert that into mathematics, first we'd say, let W represent the car's weight, right? Because they didn't give us a number for the car's weight, and so it's variable. We're not sure what that is. That would show up in an algebraic translation as W plus 700. Subtraction, right? If you say subtracted from, an example of that in English, 2 grams were subtracted from the weight. Right? Once again, we're talking about weight. And once again, they didn't tell us what the weight was. They just said 2 grams were subtracted from it. So we would say, let W represent the weight in grams, and our sentence would be W minus 2. Notice the order that comes in, right? In the sentence, it's tricky. It almost seems like we should be subtracting the weight from 2, right? But subtracted from, it means that's what you're subtracting from, right? And so when it says subtracted from the weight, that's an indicator that the weight comes first. When it comes to subtraction, it matters which one comes first. Okay. And like I said, I'd just take some time to go through these. If you're wondering how to translate a problem in your homework, something similar to it might be contained in here. So this is a good page to flip back on if you're not sure about your homework problems. So here's some more examples. Sorry, this is a much worse picture, isn't it? it's all diagonal. Multiplication, right? Let's do twice. Right? That doesn't seem like a typical multiplication word, but it definitely is, right? Twice means 2 times. Thrice means 3 times. So if your English sentence says twice the wholesale cost, well, we don't know what the cost is, so we say let C represent the wholesale cost, and our expression is 2 times C, twice C. Division divided by, right, a 2-pound coffee cake divided by 3. Oh, okay, yeah, that's what I thought. No variables are here, right? Because they tell us how much the coffee cake weighs. It's 2 pounds. Divided by 3, that's just 2 divided by 3. Okay, so yeah, I would definitely recommend kind of like just go through and browse through those and see, I just take a look at each one. Some of them don't quite apply the way that you might think they do, especially when it comes to subtraction and division. Okay. Suppose we're asked to translate these things into an algebraic expression. So the first one says, 4 inches less than Ava's height in inches. Okay, so remember, less than is an indicator of subtraction. So I'm just going to put a minus sign right here. And this is, usually you can do this. You can just kind of read straight from the sentence and almost write it directly into an equation. This one's a little bit weird just because it's a subtraction problem. But they say Ava's height. So we'll say over here, we'll say let Ava's height equal h. All right, and so how should I write this? What do you guys think?
I don't know, I was just trying to write it out myself.
Yeah,
actually.
it's weird because it's subtraction. If it was addition, this would be obvious. 4 inches less than Ava's height. There you go. Yeah, the first one. Yeah.
I had it in my head and I said it out loud.
Yeah, h minus 4. Good. Yeah, because this is a weird subtraction one, things sort of didn't work out exactly like they would in a sentence. These ones kind of do, though. So for part B, we have 18, the number. We have more than, that's an operation. And then we have a number. We don't know what number that is, so obviously that's a variable, right? Okay, so this one's easy because it's addition. So the 18 drops straight down. More than drops straight down. A number, let's call that x. There we go. Right? And so as long as it's not division or subtraction, this is really pretty straightforward. How about this one? A day's pay in dollars divided by 8. Okay, so a day's pay in dollars. They don't tell us what that is, so that should definitely be the variable. So we're just going to write over here, day's pay equals P. And you can choose a random variable. It doesn't really matter what letter you use. So we have a day's pay in dollars. We call that P divided by 8. Boom. You could also write it like this, P divided by 8. This is going to be the one that you want to get used to, though. We're going to use this old-fashioned, not old-fashioned, this, I don't know, we're going to use this other division symbol here and there, but mostly division's always going to be represented by a fraction in this class.
I hate that.
Isn't that weird? Yeah. So get used to it, right? And because I have issues with this too, right? When I see this, I'm like, oh, which one goes on the bottom again? Memorize that. Because yeah, you want to know which one goes on the bottom. Okay. A caution. I've already said this, of course. Order matters in division and subtraction, right? Subtracting 10 from 22. Whoops, almost did it wrong. Subtracting 10 from 22, right? That's not equal to, this is the not equal sign. That's not the same as having 10 minus 22, right? This one is a negative number. This one is 12. Okay, so order matters with subtraction. Okay, same thing, the same thing with division, right? If I say divide 12 by 3, 12 over 3, right? That's equal to 4. That's definitely not the same thing as 3 over 12, right? 3 over 12 is equal to 1/4. Okay. Just a couple more examples. So if I say half of some number, so 1/2, right? We know what that looks like. Of, what does of mean? You guys remember which operation was? Well, sort of.
Okay.
It's actually a trick question. That's not a fair question because of almost means both, and it's really weird the way that this works. So let me show you. So suppose we call some number x. Half of x is 1/2 times x, but we only use of for multiplication when we're multiplying by fractions, right? We wouldn't say 2 of some number, would we? We wouldn't say 100 of some number. That sounds weird. But we definitely say 1/4 of some number or 10% of some number. So of in multiplication is almost always used when the number you're multiplying by is less than 1.
Okay.
Which,
English.
and which, now this is the weird part, it is sort of like division, right? Just like you said, because this is equal to x over 2, right? And so every half of some number is kind of like division in hiding. Okay. So now this one. 7 pounds more, 7 pounds more than twice Owen's weight in pounds. Okay. That's a lot there. Okay. So we're just going to call Owen's weight W. I'm not going to write out the whole thing. So let's see now. We have 7 pounds. That's the number 7. More than. That just means plus, right? Yeah. Plus twice Owen's weight. 2W. Yeah. There we go. Let's try another one. 9 times. This is an interesting one. The difference of x and 10. So this is sort of weird. This indicates that we are going to multiply the entire difference of x and 10 by 9. And that's exactly what we're going to do. So the difference of x and 10, well, that is x, or let's see, that is 10 minus x. 9 times that, we put it in parentheses and put a 9 on the outside. Okay? This would also happen if instead of difference here, if it said the sum of, right? Then that would also happen. There'd be parentheses and you'd multiply 10 plus x by 9. Okay. Finally, 82% of last year's enrollment. Notice again, of is used when we're multiplying by a number less than 1, right? 82%, that's less than 1. So we say 82% of last year's enrollment. Let's just call that one x of x. And if you haven't learned this yet, we're going to learn it eventually. Now I convert this percentage into a decimal and multiply. So instead of 82%, I write this as 0.82. Don't worry if you haven't seen that, we're going to learn it. And that would be my final expression, is 0.82 times x. Okay. Moving on. Okay, so everything that we've talked about so far has been translating expressions. Now we're going to start translating equations. So the big difference is the equal sign. That's it. If you see algebra without an equal sign, it's an expression. If you see algebra with an equal sign, it's an equation. There are different rules for expressions and equations, right? Later on, we're going to learn a little bit about them. So here in the book, it says a little bit more about this. So here on the left side, you can see these are the expressions, and everything on the right is the properties of an equation, right? So an expression, there's no equals sign. An equation, yeah, there's definitely an equals sign. This is good. Yeah, the English phrase, like this is like an expression, the interesting book, right? We told you about a book. We didn't tell you anything about that book. We didn't give you any properties, nothing. It's just a book sitting there. Now, if we say that book was interesting, we assigned something to that book. We gave a property to that book, right? That is an equation. If we said the book has 400 pages, that would be an equation because we just told you something about that book. If we said the book is red, that would be sort of like an equation because we assigned a property to that book. Okay. In math terms, you can see like x, that's an expression. X equals 7, that's an equation. Okay. English terms. Kevin, that's just an expression. If I say Kevin is a student, that would be more like an equation because I said something about Kevin. The Seahawks, that's just an expression. It's just a football team. The Seahawks are Kevin's favorite American rules football team. That is an equation, right? I said something about the Seahawks. The number 6, that's an expression. Oops, the number 6 is divisible by 2. That's more like an equation or a statement. The students in this room would be an expression. There are 4, everybody showed up. Notice I put a question mark here. I always do that just in case people don't show up. There are 4 students in this room studying mathematics. That's more like an equation. So just like how there are words to indicate variables, there are words to indicate the equals sign. So when you're reading a sentence and one of these things pops up, it is indicating equality. Okay, so let's go over a couple examples of translating equations. So what number plus, what number, right, that's clearly going to be a variable, plus, there's my operation, 478, is, look at that, that's got to be my equals sign, 1079. Okay, so what number? I am just going to call that x plus, that's my plus sign, 478, whoops, 478 is, so I just throw my equals in there, 1019. And there we go. All right, the whole thing just translated straight down. Okay, so part B, there is a bridge in China. It's the world's highest bridge. I'm not going to attempt to say the name. Here is our equation, right? At 1,854 feet, it is, there's my equation, my equals sign, 574 feet higher than the Baluarte Bridge. Higher than, that's also my operation, right? So when these things come in like a larger paragraph, the trick is really to pick out which sentence in that paragraph is the equation contained in. They like to mess with you a little bit, especially in this book. They like to give you like this introductory stuff that doesn't matter, so be careful. They like to mess with you and throw numbers out there that don't matter too. So once you identify the sentence that your equation is going to be coming from, you just translate it directly. So at 1,854 feet, it is, Okay, that's my equals sign. 574 feet, 574, higher than, plus the Baluarte Bridge. I don't know, we'll call it B. Okay, any questions? Not too bad. Okay. Yeah, we should probably do this one. I think you have a homework problem like this. So this is one where they give us a list of data, and we're supposed to come up with an expression with this data. Okay, so they say this table lists the amount charged for several purchases from an online music store. They let A represent the amount charged, so this is how much we were charged, based on buying this many songs. They say, find an equation giving A in terms of N. Okay. So, A is the total amount charged, right? Let's just write this out. So, they want to give us an equation that says total, right, and some based on total amount based on some equation with the number of songs, right? So all I need to do to start this off is figure out how much we're paying per song here. So I do my first line first, and I say if they charged us $1.98 and we bought 2 songs, I punch in 1.98 on my calculator, or by hand if you like that stuff. That equals 99, right? And so on that first line, a song costs us 99 cents. Let's make sure that's the case for another line too, just so that we know it doesn't change as we move along. So let's do the last line. The last line says they got charged $9.90 for buying 10 songs. So let's see now. 9.9 divided by 10.99. Yeah, so I think they're charging us 99 cents per song. Okay? So now, if I was going to come up with an expression for the total amount charged based on how many songs I order, what would that be? Anybody got any ideas? What if I bought, what's the number that's not on here? What if I bought 4 songs? How could I figure out how much they were going to charge me for that?
You divide the 2, charge by something.
Right? That's how you figure out how much you're getting charged per song, right? Yeah. We got that though, right? And we say, okay, we know exactly how much they're charging per song. So we say, yeah, exactly. We say, well, what if we bought 4 songs? Well, it'd be 4 times 0.99. Well, what if we bought 20 songs? Then it'd be 20 times 0.99, right? We keep going. What if we bought 500 songs? You get the picture. So the total amount is however many songs we bought, N times 0.99. Does that make sense?
I zoned out for a second, put it out right now.
And just so you guys know, something a little bit weird up here. I usually, it's preferred to write the number in front. A lot of times I'll do this just because I'm talking and not thinking about it, but when I write my final answer, I always put it like this, 0.99N. Usually the number goes in front. That doesn't mean it's incorrect if it goes in the back, right? This is not incorrect. That's just not the preferred way that people write things. You know, like if you go into your next math class and write everything like that, like Colleen will be like, what is happening?
I'd like to become a mathematician just so I can do that.
You can't. That's the great thing about being a mathematician. Yeah. If you're good enough, you get to make your own notation, right? And you get to use the notation the way you want.
And other mathematicians look at it and just like, screw you.
Yeah. Like what? You're not good at, you're not a good enough mathematician? Mathematicians get testy about that. There's a great story about two astronomers who are both like mathematicians, and they got into a big argument over who was the better mathematician. So they decided to have a sword fight over it, and one of them cut the other's nose off. Yeah. Right? Oh man, right? And I try and picture that, and I'm like, what did he say Like, was he like, ha, division? Like, what did he say when he sliced the nose off? Did he say some cool math term? What was it, right? Minus your nose. Yeah.
I can't, yeah. But I'm working for that when I get back there.
You just chopped everybody's nose off.
Right, this is what I learned in algebra. Yeah.
This is the only thing I did in
Okay, all right, so now we're gonna go over section 1.2. I do see that we're about 20 minutes before the end of class, so I might be rushing just a little bit in this. So these are the laws of algebra, right? These aren't quite the most basic laws in algebra, but they're very close. Everything that we do from here on out, if we were in like a really rigorous algebra class, like, you know, if we were in like, I don't know, grad school at Harvard or something like that, we would have to prove everything we do from here on out based on these basic laws. And they'd say, if you haven't proved it yet based on these laws, you're not allowed to use it. It's harsh. In this class, we don't do that. We just introduce formulas. You can use them freely. But in like a hardcore math class, that's what they do. They say, these are the basics. Now you have to use logic to create all the math we're about to use. We don't do that here yet. But someday, some of you guys might. You never know. Okay.
I'm pretty sure the Enigma code is broken.
The Enigma code, that's a good one, actually. Have you heard the whole story about that? Yeah, so if you guys don't know what the Enigma was, it was a machine made in World War II to make really complex codes for the Nazis. They said that nobody could break it, and it was unbreakable, right? And they calculated the number of combinations possible in the Enigma machine was in the trillions, I think. It was ridiculous. And so if you brute forced it and tried to put it into a computer, which they didn't really have back then, it would take months to break a very simple code. Well, there were some mathematicians who took a look at the Enigma code and said there's two things that are going to help us out. One is psychology. Right? One is that we know that the Germans greet each other with the same phrase every time they log in, and so we can decode that. And another, these mathematicians figured out this weird little logical exploit that allowed them to bypass like 80% of the possible codes. It was just based on this strange bit of logic. This guy said, well, wait a minute, what if we look at it like this? We can eliminate 80% of these, right? And then they could feed it into the newest computers and solve it. So yeah, just a little bit of mathematical logic can bypass a massive amount of work by computers. I love that story.
Insider knowledge.
Yeah. I can't remember if there was a lot of insider knowledge. There's probably some of it. I know that a few machines actually like made it out of Germany, and so they were able to like reverse engineer certain parts of them, and I think that's how they found the logical exploit in the first place.
It also helped create cell phones of today. So.
Right. Yeah, and was it The Imitation Game? Was that the movie they made of it? Yeah, there's a very sad movie called it's exciting and sad, called The Imitation Game, about the guy who made sort of the first computer, but he was persecuted because he was a homosexual. That's very sad because he was brilliant. Okay. Yeah, very much, very much. Okay, now that I've blabbed a little bit, I like to go on tangents about stuff. Let's talk about these laws. So, I already went over this stuff. Yeah, these laws, these are going to tell us how numbers are allowed to interact, right? And they're also going to give us the rules around using parentheses and things like that, okay? So the first law we're going to go over is called the commutative laws. So just recall from arithmetic that when we do addition and multiplication, order does not matter. That's because these two operations are called commutative. Okay, so when an operation is commutative, that means that it can flip back and forth and it does not matter. Okay, so subtraction is not commutative, neither is division. Only addition and multiplication.
Wait, what did you say about the flip back and forth?
It just, commutative just means that you can flip them back and forth, and it doesn't change. I got you. No, that's
what I'm writing down. Wait, what?
yeah, yeah. As long as it's multiplication or addition, you can flip it back and forth, and that's what it means to be commutative. So, like in your homework, there's some problems that don't think too far into them. They just say, write an equivalent expression to this, right? And you say, well, what? How do I even do that? Use the commutative laws and just flip them. It's really that simple. 5 plus y instead of y plus 5, okay? You know, obviously on this one on your homework, I'm not going to be a stickler if you don't show your work, right? What work is there to show on this? Right, okay? Yeah. So for this one, 9x, I can write this as x9 instead. This one's interesting. I can write this in a couple different ways, right? I can write AB plus 7, reverse the addition. I could also write this as BA plus 7, right? Flip the multiplication as well. So that's what it means to be commutative. Now let's go over the associative law. So the associative law, this tells you how parentheses are allowed to move in multiplication and addition. The associative law says that if all your operations are multiplication or they're all addition, the parentheses can move anywhere you want them to. It doesn't matter. Or they can go away completely. Right? And so these two examples, you can see I had parentheses around the 2 and 7. That's the exact same thing as if I had the parentheses around the 4 and the 2, which is the exact same thing if I just removed all of them. However, if there's a subtraction sign in there, that doesn't work anymore. Can't do that. Same thing with multiplication. See how I can just move these parentheses anywhere I want. On the 2 and the 7, the 4 and the 2, or just get rid of them completely. I know, you guys are saying, so what for that one? That one's not used as much. Okay. But remember, if it's division or subtraction, be careful about just getting rid of parentheses. If I'm ever going too fast up here, let me know, okay? Sometimes I get a little bit excited. Okay. So, in your homework, if you're asked to use an associative law to rewrite an expression like these, all you do is move the parentheses around or get rid of them entirely if you want to. That's totally fine. So with this first one, I just put the parentheses around the y and the z instead. Boom, done. With this other one, right, maybe I'll just leave the 8 out and put the parentheses around the x and the y. Okay, you guys need to know that. Oh, yeah, that's right. This is a bad example, but hold on. Get rid of that one. So when these two operations are used together, this does not always count, right? And so even though I have nothing but multiplication and addition here, right, this is not a case where I could move the parentheses around because multiplication exists and addition exist here together. There's weirdness that goes on, right? And so if it's two parentheses multiplied together like this, you can't just remove them. If there was a plus sign in the middle, though, then it'd be fine.
You could switch them, right?
Yes, good. Yeah, exactly. You could definitely use the commutative. X plus 4, yeah, there you go. 3 plus 5, good. Okay.
Are they going to try and trick us with that?
Probably.
Oh. I hate that. I work so hard and then I'm like, oh.
And also, so I may annoy you with some of my tests then, because that is one of my favorite things to do is like make something look really ugly unless you remember something from class that we learned that you can get rid of it all, right?
Well,
like
if I ever storm out, I promise I'll come right back.
Okay.
I just need a moment.
Okay.
I used to do that, and then my teacher just got so used to it in high school.
That's so funny.
She's like, just give her a
just take a beat.
Be like, okay, explain this to me again.
Nice. All right, so that one's the associative law. Let's go into distributive. Notice I have a little star up here. That's because this is the most important law that we're going to study today. So the distributive law tells us how to deal with parentheses and multiplication, right? The distribution law would teach us how to multiply that last weird example that we saw. So before we go fully into the distribution law, though, let's go over, let's see now, there we go. Let's go over what terms and factors are. So when we talk about a term in an algebraic expression, a term is everything separated by addition or subtraction. Okay, so this first example here has 3 terms. 3s is one term, st is another term, and 2s over t is the third term. Okay, so those are terms, right? If I say x plus y plus, I don't know, zk, right? There's 1, 2, 3 terms in this as well. Then there's the factors, right? The factors, instead of parts of multiplication, or instead of parts of addition and subtraction, the factors are parts of multiplication. And so this is one factor of this expression. This is another factor of this expression. If I say 33x, y, z, I have one factor here, one factor here, one factor here, and one factor here. Right? So each thing that you're multiplying in is considered a factor.
Okay, not a term.
Not a term.
Okay, I zoned out for like 1 second while I was writing.
Yeah, terms have addition or subtraction in between. Factors have multiplication in between. Okay. So that leads us to the distributive law. So the distributive law says if you have 2 terms that are in parentheses, right, and there's a factor out front, what you do is you multiply each term in those parentheses by the factor out front. And so I like to draw these little arcs. Right, you can see here the A has been multiplied by the B, and the A has been multiplied by the C. Right? And so that's what we call distribution. As in, we distribute that coefficient into all the terms. That's going to come up everywhere. You're going to be distributing just a ton. And then later, we're going to learn about factoring, which is the reverse of distribution. But for right now, we'll focus on distribution. So, for our first example of distribution, we have this guy here. 3 times the sum x plus 2. Right? Okay, so if I'm asked to multiply this, first thing I do, I multiply 3 by the first term. That gives me 3x. Then, I keep whatever symbol's in here, and I multiply 3 by the next term. 3 times 2 is 6, 3x plus 6, and I'm done. If there's more than 2 terms in there, you multiply by all of them, right? Even if there's 14 terms in there, which hopefully I won't give you something like that. If I do, you could curse me, that'd be fine, I deserve it. But you just multiply by everything. Like in this example. Yeah, right? You'd be like, you said we could curse you. Right? And so see this example has 3 terms inside the parentheses. So we're going to do 3 multiplications for this. The first one, 6 times s, 6s. The next multiplication, 6 times 2, plus 12. And I'm going to go back and I'm going to rewrite my s, because that looks like a 65. That's another thing that I do very poorly is s's and 5s. Okay, so I've done my second multiplication, and now my third multiplication. 6 times 5w. We haven't quite gone over this yet, but when you're multiplying a regular number and something attached to the variable, you just multiply the coefficient and the regular number and then leave the variable, right? And so 6 times 5 is 30, so this is 30W. Yeah, and in these first couple of chapters, there's a few operations that we're doing that we haven't quite studied yet. And so if there's any weirdness, you know, don't hesitate to ask me in class, or, you know, it will come back up later.
Just send you an email. Like,
you can do that too. Yeah, that's totally fine. Yeah, no, I actually, that is allowed. If any of you guys study at home, you can totally send me screenshots, send me emails, and just say, you know, the response time might not be immediate, but as soon as I read it, I will try and figure it out and send you at least some help with it. So it's totally fine. Ah, Noelle! Noelle is so much fun to have in class. She's great. Okay, so this one looks a little bit weird, right? Because the number's on the other side. But remember commutation. Yeah, so remember commutation, right? Commutation says we could actually write this 5 over on the other side if we wanted to, right? And then we'd just distribute in the normal way. So you could rewrite it on the other side, or you could just distribute from this side and it would be fine. So I have 5 times C, that gives me 5C, and then I have 5 times 4, that gives me 20. Okay, and just remember distribution, right? This right here is probably the most common mistake that I see in this class. Notice how this person being me, this person forgot to multiply the 4 into the 2 back here, right? Whoops, that's a dark color. That's a really dark color. Okay, yeah, right? What a jerk. Yeah, this person multiplied the 4 into the x, but not into the 2. So this is not correct, right? You got to do every term in the parentheses, or it does not work. As for this one, what was this one for? Oh, that's right.
like, this looks right.
No, they are both right. This is just to show you. So there's a little bit of a difference here, right? You distribute when there's an addition or subtraction sign in the parentheses. When it's just a multiplication, there's no distribution necessary. Okay, and so remember that problem where we multiplied 6 by 5w? This is the same concept, right? And so when I say 3 times 4y, since this is multiplication inside here, I don't distribute this, right? It's multiplication. So these are commutative. So I can rewrite this as 3 times 4 times y, which gives me 12y. Okay, whereas in this one up here, I actually distribute to each term. Okay, so if there's addition in the parentheses, got to distribute. If it's nothing but multiplication, just multiply the numbers together. No distribution necessary. Okay. And let's see now. Yeah, we should go over factoring real quick. So, so the distributive law explains the operation of multiplication, right? That's kind of what we went into. The opposite of the distributive law is called factoring. That is factoring an expression. A factor, to factor something is basically, you know, like you're pulling a single factor out of multiple terms, right? And so let's do a distribution on this example. Right? So on this example, I'd multiply the 3 by x to get 3x. Then I'd multiply the 3 by 4 to get 12. Okay. Now, if I'm asked to factor that exact same thing, what I need to recognize is that this 12 contains a hidden factor of 3, right? And so I want to rewrite this. So I rewrite this as 3 times x plus 3 times 4, right? Notice how 3 times 4 equals 12, right? So I'm not changing the value of that. And I just recognize here that each of these terms contains a 3. So I pull those out. So on my next line, I write my 3 out front, and then in parentheses, I write these terms that I had left after I factored my 3's out, x plus 4. That one's a little bit weird. Factoring is weird. So here's a good example of factoring. This one here, 3x plus 3y. I can see right off the bat my common factor is 3. I have a 3 here, and I have a 3 here. If I had some other term that didn't contain a 3, I could not factor 3 out of here. Since all my terms contain that 3, I can pull it out, right? And so instead of multiplying it in, we pull it out and we write it out front. So I have 3 times x plus y. If you want to check your work on these ones, you can distribute that 3 back in and make sure you got the same expression as you started with. If you get something else, something went wrong. This is an important one. A little star by this one. So we take a look at each term. I see that this term contains a 7. This term is a 7. And 21
divisible by 7.
Boom, you got it. So we know that there's a 7 in each term, right? So we rewrite it to show that. Okay, so I have my 7 times x here. That's plus 7 times 3 y. And that's plus, this is a key here, right? This is one that is weird. 7, super important, 7 times 1.
Okay, so just clarifying still a little bit. If you, in your mind, you wanted to, you could put those in parentheses just to keep them all.
Yes.
Okay.
Yeah. The notation that I'm using up here is, I like it, but if you find that things organize in your brain differently and it helps to use parentheses in certain places, do that as long as it's proper math. So now that I see that each term contains a 7, I'm allowed to pull a 7 out. So I write it out front, and then in parentheses, I fill it in with whatever was left, right? And so this is x plus 3y, and this is the key, plus 1. Okay, so when you have a solo number like that, like this little 7 hanging out here, hey, how's it going?
There, it's Math 105.
Oh, we're not starting yet. They're not starting yet for a little bit.
Perfect, thanks.
Yeah. So after we pull the 7 out, right, we just have to remember there's a little 1 there. That's kind of like a placeholder, right? And so you'll notice if we check our work on this and distribute the 7 back in, we get 7x plus 21y plus 7. See, if we didn't have this plus 1 back here, we wouldn't have this plus 7 back here, and we wouldn't have the correct answer. So that's it. So I'm sorry that we had to rush through that last little bit. Yeah, any questions? All right, thank you very much for your patience. I will try and put this up on the web by tomorrow, and we'll have class at 3 tomorrow.